Hello everyone, thank you so much for joining us today. I'm Haoxiang Yu. You can also call me Steven. I'm a first-year PhD student in the University of Texas at Austin. I'm here to present our research work, Phototyping Opportunistic Learning in Research-Constrained Mobile Devices. This work is contributed with Xiaoyan Chen, Sansu Li, Dr. Xi Zheng, and Dr. Christine Julian. Let me briefly discuss our agenda today. I will first give a brief introduction of our paper. Then, I will go through some important related work before diving into the detail about our system design of our phototype. Next, I will discuss about the flexibility of the opportunistic learning, which including our evaluation results. Finally, I will discuss the challenge and give a conclusion. Mobile devices today are enriched of variety kind of data, and most importantly, the private data. This may include text messages, photos, healthcare data, and personal using preference, and so on. This data can be leveraged to train the model to support subsequent user interaction. Consider a model on user's smartphone that can identify the object of the photo to allow the keyword search over the photo library. Training such model is clearly requires a very large number of labeled photos. However, in traditional machine learning technique, the data would have to upload to a central server, which may violate users' privacy. In recent years, the federated learning got a lot of attention from the research community, which it still requires a central server to assist with the model training process. Last year, our research group proposed a new technique named Opportunistic Learning, which does not need a central server anymore, and could perform a training based on the user's encounter. In this paper, we implement opportunistic learning framework on real mobile devices and evaluate the real performance and the feasibility of the system. I do want to make a note here. Our neural contribution does not necessarily to put the focus on the evaluate accuracy of our opportunistic learning, but rather the practical feasibility of the opportunistic learning, and in general on mobile devices. This is due to the limitation of the mobile devices and testing environment we have access to. During time we compressed to the paper, the limited number of the mobile device made it unreasonable and impossible to further evaluate the accuracy for the system. However, when we look into the future, testing a system using large amount of mobile devices as a testbed would be one of the possible research direction. Therefore, we fix the learning model and focus on the two key challenges, which we'll discover later. In particular, we use a basic opportunistic learning approach, which proposed in the previous paper. Look at the illustration on the right. In such a framework, we have one device called learner, and an encounter device called neighbor. The learner will ask the encounter neighbor to perform the round of training by using the neighbor's computational resources and local data. While the neighbor maintains the privacy of the data, the learner can leave the advantages for different data and to train the model. In addition, recognizing the difference in devices in pervasive computing environments, we set different personalized learning goal. When the learner discovers a new neighbor, the learner can use information about that neighbor's local data distribution to determine whether to collaboration with will be benefit or not. If the learner decided to request the collaboration, it then will send the model to the neighbor. The neighbor, as a result, will perform the round of training of the learner model, and then send back the training result. After that, the learner will update the system. Before I go further into detail about our system design of the new learning approach, I want to discuss some important related work along with the two framing challenges. The first one is how to support on-device training, and the second one is using device-to-device communication to exchange the model summaries. For on-device training, with a growing interest in this area, some platforms also trying to build the tools that support on-device training. In particular, there are 5 major tools that bring our attention. The first one is the Tensorflow Lite, which belongs to the Tensorflow family. It does support Android and iOS on-device inferencing. However, when we compress the paper, the Tensorflow Lite hasn't been able to support on-device training yet. PyTorch Mobile belongs to a PyTorch family and also support on-device inferencing with Android and iOS devices. Yet, it does not support on-device training either. The third choice is the one we use in this paper, named CoreML. It's made by Apple. But this one only supports iOS devices. The good part is, this is one of the tools that support on-device training when we run the experiment and write this paper. However, it still has some limitation. The on-device training part only supports convolutional neural network and some dense network. The fourth one is TensorFlow Federated, TFF. It is designed to evaluate the distributed learning with focus on setting under federated learning. The drawback, as the previous one, this one does not support any on-device training. The last one is Openmind. It is an open-source ecosystem that supports federated learning framework. However, it still needs a central server to perform the computations. Communication-wide. In opportunistic learning framework, devices need to discover each other and exchange information to support on-device training. For today's mobile devices, there are 2 major methods that we can perform the model neighbor discovery and model exchange. The first one is Bluetooth Personal Area Network, and the second one is a peer-to-peer Wi-Fi. Due to the limitation brought by the on-device training part, which only allows us to work on iOS using the CoreML framework as we talked about earlier, we focus on what kind of tasks the iOS system can perform. There is a framework called Multi-Peer Connectivity Framework, provided by iOS system, combines the Wi-Fi network, peer-to-peer Wi-Fi, and with a Bluetooth Personal Area Network. Let me re-emphasize the goal of this paper. We are trying to identify the challenge in implementing opportunistic learning in real-world devices. For the purpose of our experiment, we are using a straightforward implementation of the opportunistic learning based on our previous paper, which apply a classification task. In this task, each device has a personalized learning goal, and it is captured by a set of data labels. The device model should be able to classify it correctly. In addition, each device continuously collects or labels data based on the user's behavior. In the illustration on the right, first, each device continuously shares the advertisement that's including the local label distribution. When one learner discovers a neighbor, it determines whether the neighbor has the label what he wants, or whether it is in the learner goal set. If it does, the learner should be able to benefit from the train on the neighbor's data. However, because the neighbor does not want to share the privacy information with the learner would, instead, share the model with the neighbor. The neighbor can load the model into the memory and provide a small batch training using the learner's model and its own local data. Finally, when the training run completes, the neighbor would turn the set of updated weight to the learner. What's more, as we discussed earlier, the CoreML is a machine learning framework we are choosing for the system design. It offers on-device training and device inferencing that has the power of the low level of hardware and implemented by the performance of the GPU and Apple's AI accelerator. Within our prototype using the PeRConAI, we must solve two particular questions. First, how to extract the minimum model that represent and can be shared between the learner and the neighbor. Secondly, how to perform the training on the neighbor's device. For extracting the model, the PeRConAI relies on the internal compiled model representation. It's stored in the .ml model C file. You can find its high-level structure on the left of the screen. This particular format has difficulty to extract the model weight and share with the neighbor. To minimize the resources consumption during the model exchange, we prefer to only share the portion of the file that contains the updated weight. To determine the portions that need to be shared, we compute and compare the empty file hash volume, each internal file before, during, and after the training process. We find that only 3 highlighted files has been changed during the training. As a result, we assume that those files are the files that contain the updated weight and need to be shared with the learner or neighbor. For the second challenge, how to train the model on the neighbor's devices. When the neighbor device receives the model from the learner, it will load the model to the PeRConAI and train it on its own data. In the result, for each encounter, the neighbor trained 10 epochs of the model using its own data. When the training process is complete, the neighbor device will extract the updated weight information from the .ml model C file and send it back to the learner. After the learner receives the updated weight from the neighbor, the learner will review the model and use it for inference. To measure the performance of opportunistic learning on real devices, we deploy our model on 7 different Apple devices. We use a customized version of VJJ16 to tolerate the input of a CIFAR10 dataset, while satisfy the memory limitation of our testing devices. Each device is using a VJJ16 model initialized with a random weight. Each device randomly selects 2 out of 10 labels, then receives 300 different images from 2 labels. Each device also randomly selects 2 labels as their goal distribution. This table shows device we are used. We are trying to use a different type of device to trying to see the difference in the real-world environments. The devices are arranged within the communication range for each other in the entire experiment. With the exception of the iPhone SE, the device has other applications installed. They are everyday devices from real individuals as we are trying to simulate the real-world environment as close as possible. But before the experiment, we close all of applications other than our testing lab. But some background tasks may be avoidable to prevent on the device. In remember of this session, we report the benchmark measurement for 2 stages of the opportunistic learning: device-to-device communication and on-device training. Across both challenges, we found that device thermostat states are significant impact on the performance. Apple defines the thermostat for a device with 4 different levels. Nominal, which is the device temperature is low, the device can finish as much work as needed. Second is fair, which device temperature is slightly high. The Apple suggests the developer to reduce resource usage. And serious, which device temperature is high. At this level, Apple suggests developer to reduce the CPU and GPU usage, I/O operation, and the network, and also the Bluetooth usage. The last level is critical level. In this level, the device needs to cool down immediately. Most of the work will be a serious impact or even terminated. This figure reports average time required to perform the communication steps, parsed by device-to-device communication and by the thermostats for each device. The time of the discover new developer is calculated as the difference between the neighbor device being online and its neighbor discovered by the learner device. The time to establish the connection is measured as the time between the learner sending the invitation to the neighbor and the connection being fully established. Finally, the time to exchange the model is measured as the difference between the one device begins send the model and the second device completely receive all of them. The figure A shows that when the learner on the critical states, the speed of discovery is serious impact. However, the thermostat for the neighbor device has a limited impact on discovery time. The B shows that the thermostat has a little impact on the time establish a connection. The figure C shows that when either of the device thermostat become more critical, the time of the exchange will impact more. This is to be expected since both devices has a computational role to play in the model exchange. This figure shows the training time and the thermostat for each device over the experiment. Each measurement reports the time for each epoch. The background of colors in each figure represents the thermostat for the device during the training. The next figure shows that the same result, but is on the different device level. Because the newer device SoC has a higher efficiency than the older device, we observe that the older device needs much more training time and is much likely to jump to the fair level or even higher thermostat level. Our phototypes and the experiment has shown that it is feasible to implement opportunistic learning in real-world device and device-to-device network. However, there remain open challenge and opportunity for further innovation. As we discussed in related work session, there are limited frameworks that support the particular implementation for on-device training. In addition, even though it is the most stable and available of the on-device training framework, the core ML can only support a limited layer of on-device training. In particular, for now, we can only use the traditional CNN layer and dense layer to do the on-device training. We checked the ability to support the MobileNet and MobileNet V2 as they are designed for the mobile environment, but neither of those models can be used in a core ML framework. Further, it is well known that mobile devices are resource constrained and their operating systems are designed to monitor the system performance and adapt on fly when the performance changed. The system-level adaptation can influence the memory and computational intensive during the training scheme. For the purpose of this study, we have to dramatically reduce the size of models that we trained. In the future, the operation system could be made more train-aware and collaborative in the on-device training process. Finally, the previous figure shows a large difference in on-device training for different devices. Given those dramatic differences, and the expected continuance of the fragment in the mobile device market, the ability for opportunistic learning framework to be able to handle the huge device difference is important. Future work should consider adapting the model size and the training intensity based on the individual device computational capacity. We demonstrated the feasibility of implementing the two key factors of opportunistic distributed machine learning, supporting localized device-to-device sharing data and on-device training with the real model. In the process, we identified several limitations of the existing platform and several opportunities for future contribution with a significantly partial impact. Our effort demonstrates that it is essential for on-device learning scheme directly consider more than just the hyperspherical memory, computation, and bandwidth specification of devices. One must also consider the interplay of those constraints, as well as the way the model training and communication interact with other functions on the device. We also identify several other future system work in supporting opportunistic learning. First, clearly, platform special solutions are limiting, and we must seeking a framework that supports cross-platform contribute learning. Second, fragmentation in the mobile device space is a very real issue, and the performance for on-device training on device is different dramatically. Opportunistic learning implementation must consider those device different